So now we will discuss the second part of this, second section of the second part. Okay, so we're still in oscillation. So we will have maybe 3.5 lectures on oscillations in non-autonomous systems. So this means that something depends on time explicitly. So now, the first example, we will consider several examples, more or less general, just to have an idea what it is. So first today, I'll talk about the resonance, which is rather elementary part. And then we start to consider the parametric resonance. Okay, so first example we consider is the first class of the system are linear systems. So linear systems usually appear when you consider small oscillations in equilibrium, remember? So, but now we put some periodic parts, so we will put with periodic forcing. With periodic forcing. So the simplest example is probably the linear oscillator, mass and spring with coefficient k, no gravity, nothing, and we have a coordinate x, and then we put force. F of t is we force the mass by external force. So the force we'll consider this periodic force, and to make it simple, we will just take it harmonic. So the F0 constant by cosine omega t. Omega is frequency, F0 is amplitude. So let's find the solution of this system. So just to begin with. Okay, so this is harmonic. So this is forced harmonic oscillator. And well, the fact that there is a time dependence of something in the formulation already means that energy is not conserved. So automatically, you can compute energy, but it will not be conserved in time. And the equation of motion, we know what it is. So the equation of motion of a spring is m mass by acceleration plus constant elastic constant of the spring by x, where x is computed from the equilibrium, and then the force you put on the right hand side as usual. So that's equation of motion. We divide it by m, and you get x double dot plus here there will be positive coefficients, so we call it omega squared. And here F0 by m we call A cosine omega t. So what we defined is omega squared was k over m, and amplitude is F0 over m. So how to solve these equations? So let's solve this is equation we will solve first. Okay, so first let's prove a simple thing, that proposition will say that general solution is x of t. It can be decomposed in two pieces. So there will be one xp plus xa. So where xp is any, in principle, but any fixed, but any particular solution. So you take any particular solution xp of t, so any solution of the system, and add a general solution and xat is a general solution of the autonomous system. Autonomous means when you just no forcing. So that's extremely convenient because you reduce the solution of this system to solving the system without right-hand side, which we already know how to solve, and finding just any solution to this full system. So you just need to find the full solution. So the proof essentially, the proof is so if for xt xp plus xa, then what you can compute? Let's compute the second derivative. So second derivative of x is second derivative of p plus second derivative of a, but now we know that. No, let's just verify that equation of motion is satisfied. So x double dot plus omega squared x double dot is what? We substitute the sum, so it will be xp double dot plus omega square xp, and then xa double dot plus omega square xa. So now we know that this is particular solution, so this should be equal to a cosine omega t. And this we know it's 0 because it's solution of the autonomous system. So we know that if x is represented in this form, it's always a solution. And now if any, let's say, x tilde is a solution, then we just have to check that xka, which is different, or we don't need even to put it tilde. So if x is a solution, then we have to check that if we subtract xp, that it should be a solution of the autonomous system. So it solves the system xa double dot. So just compute. Let's compute this expression. So where you put that, and well, that's exactly the same calculation. So it will be x double dot plus omega squared x double dot minus xp double dot plus omega square xp. And this is a cosine omega t, yeah, because we assume it's solution. This is also solution, particular solution. So it's 0. So this is what we proved. Essentially, we proved in both directions. So we proved that whenever you have x in this form, it's a solution, and whenever you have a solution, it can be put in this form. So that's very simple statement. Okay, so then we can just use this statement in order to solve this system. So general solution we already know. So general solution of the autonomous system we know that it is cosine small omega t plus any phase. So for any prefactor and any phase, any angle. So general solution we know, so we know the second part. So it remains to find the particular solution. So how you do it? The simplest way is to, well, we know what it is already from the series, so we just say that let's guess it. Let's guess that solution. Let's take a solution in this form, which is unknown coefficient cosine omega t. Because we know that on the right-hand side we have a cosine, and if we have take x in the form of cosine, there will be cosine here and second derivative cosine, so it's compatible. So when you substitute to the solution, to the equation, so what you have, second derivative will be minus b omega squared cosine omega t. Then it will be plus omega squared b cosine omega t. So that's left-hand side of this equation, and the right-hand side is a cosine omega t. So cosines cancel. Then you have, let's flip the terms. And this gives you b. If the denominator is not 0. So we found particular solution in this form with a coefficient b, which is given by amplitude of the forcing and the difference of squares of the amplitudes. So the graph of this function is, so if you want to see b, which is amplitude of the solution as a function of omega, then you will see that there is special value. So the frequency of force, when it is equal to the natural frequency of the oscillator, the graph diverges. So this is what's called resonance. So what we see, if you force oscillator, it has two pieces of the solution. One piece is just its usual oscillations with its proper frequency, small omega. And the second part which you add is the oscillations with the frequency of the forcing. And now the amplitude can become very, very big if the frequencies are close to each other. So if you force a pendulum with a frequency which is close to its own frequency, it will become, the amplitude becomes very large. Good. So that's resonance. So now we can analyze some properties of this general solution. So first what we do is, let's consider oscillations near the resonance. So when the frequencies of force and pendulum are very close, from the rest. When the position is 0 initially and velocity is 0. So let's take the oscillator which is in the rest and now start to force it. And let's see how it will, what will be the solution. So we will find, okay, so what we do? Okay, so our solution is the sum of the two, right? So it's c cosine small omega t is phi plus b cosine large omega t. So that's our solution. And what we know is the two frequencies are close. So what we do is we define epsilon, which is difference. So this difference is much smaller than frequency. So that means that they're very close. Yeah? So that this condition we just wrote in the explicit form. Okay, and now we can express. Let's express what this term means. So essentially, what we need to find the solution. Essentially, the solution has just two free parameters, the c and phi. So we need to find the solution which satisfies this initial condition. And we will do it in approximate way, assuming that the difference between frequencies is small. So we are close to resonance. Okay, so let's consider first this term. So b cosine omega t. And let's put, so b is this, right? Omega squared minus, and large omega is small omega plus epsilon squared. And then we have cosine, and that will be omega is omega t plus epsilon t. Okay, so you open denominator, be long expression. So omega square will cancel, so it will be minus, so I put minus here. 2 omega epsilon minus plus epsilon squared. And then you open cosine of the sum. So it will be cosine omega t, cosine epsilon t. I think minus, no, it should be minus, yes. Minus. Remember this formula, right? How to write cosine of the sum. So now what we do, now the next step is to write the approximate relation when epsilon is small. So we will neglect everything which is smaller order than epsilon. So we can remove epsilon square here because it's much smaller than the first term. So now cosine epsilon t can be written as 1 plus small o of epsilon, because next term is epsilon squared, right, in the cosine. In expansion of cosine, it's 1 plus then epsilon squared. Some coefficient. Okay, a sine is epsilon t plus higher order term, right? So what at the end we have is minus, so approximately minus a over 2 omega epsilon cosine omega t minus epsilon t sine omega t. Good. So now we know what to do, because okay, let's open the parentheses. So it will be minus a over 2 omega epsilon cosine omega t plus epsilon cancels, you see, so it will become a over 2 omega t sine omega t. So you see this part already is 0 at the beginning, and its derivative is also 0. And this part has the same shape as the autonomous solution. So what we can take C to be just this A over 2 omega epsilon and phi equal to 0. And then we put them together. This term will cancel. Right? And we get a solution. It's A over 2 omega t. So you see what happens with the solution is that as time grows, there is a linear growth of the amplitude. Right, so this is a t over 2 omega, and this is minus a t over 2 omega. And then there is a t by t sign. So it's this is what happens with the pendulum when you start oscillating it at the frequency close to the resonance. So this amplitude grows linearly in time. So this is usual resonance. What you can check that this formula is valid if. So what we did, you see here epsilon was small, it's okay, but so important part was this epsilon t, because the real expansion is O of epsilon t, and this is O epsilon t. So the small, what have to be small to make this step is epsilon t should be small. So it's valid whatever epsilon t is small. Or the same is that, smaller, that t is much smaller than 1 over epsilon. So when you're very close to resonance, so epsilon is small. So for some large t, this is correct solution. And whenever you're exactly at the resonance, this will be just will grow forever. Okay, so that's solution at the resonance at small times. So the next, what is also good to look at is a solution at large times. So what happens if you wait longer? Okay, so if you wait longer, then you cannot make these simplifications, and we just have to work directly with this solution. So let's see what it gives. So for large times, for larger times, we just can directly see this. Let's just compute what this solution means. So this is general autonomous plus particular solution. And let's just take a sum of the two. So remember, so here we had so it was omega plus epsilon t. Yeah, so that's the solution near the resonance. But let's not make any simplification. Let's take a sum. So how you take a sum of two cosines? The way I like it is what you do is you write, this is the real part of exponent Right? So the exponent of I by this argument, real part, is just cosine. And then you take this also, you take real part. B is real, so it will be exponent of t. And then we can remove exponent of omega t. So ei omega. Let's remove it later. So let's keep what will be left. Exponent I phi plus b exponent of I epsilon t. So this is first part, and then it will be I omega t. Like this. Correct? Yeah. And now what we do, we call this first part as its real, its absolute value we will call A, capital, and the phase we will call psi. So this gives you real part of AT exponent I omega t plus psi t. And this is finally, now it's cosine again. So this is our general solution. So what you can see is that we have the solution near the resonance. It oscillates with the frequency of the nearby, with the frequency almost the frequency of the pendulum. But then there is a drift of the phase and drift of the amplitude. But both are slow. So these are slow functions. They are slow functions because they depend on time only through epsilon t, where epsilon is small. Because they depend on epsilon t. So in order to have large change of A, you need to have t which is as large as 1 over epsilon. So you need very large t in order to have any change, any visible change in this function. So that's our result. And so what remains is to see what exactly A is. What really A is. So what we will compute is, so what's important is what, so what is A? A is absolute value of this quantity. So let's compute. Okay. Let's compute modulus of A. Modulo of A squared is what? Is the absolute value of this, which is C phi squared. So the squared absolute value is the real part squared plus imaginary part squared. So this is real part is C cosine phi plus B cosine epsilon t squared. And imaginary part C sine t squared. So when you open the square, so it will be C squared cosine squared plus C squared cosine squared. So just C squared. The same with B squared. And then there will be cross terms, which are 2bc. And from the first, it will be product of cosines. From the second, products of sines. And this is cosine of the difference. So this becomes c squared. So that's our formula. So we found what is the squared amplitude. And what you can see, so what you can see is that this value is changing periodically between the value which is difference c. So what you can see is that the square is changing between. So assume that c and b both positive, right? So then it changes between c minus b and c plus b, right? Okay. You agree? So then that gives us finest form of the solution. So first of all, we have a amplitude. Modulus of amplitude, it oscillates between two values. C1 is modulus c plus b, another modulus c minus b. So here we assume that BC, they're both positive. If they're not positive, you just make slight modification of this formula. So between the two values, so what you have for A, it's just slowly changing function. So this is A squared, right? This is good. So squared amplitude. And then the solution itself. So now what happens? So we have to put, so this is, no, this is A. So it's not cosine, it's square root of this quantity. It's not exactly the cosine. And then for x, it will have, so what we have to write this amplitude. And we will write the same amplitude below, symmetrically. Right. So this is A of t, and this is minus A of t. And then the solution will, you still have to take A and multiply by so A which is low, and multiply by cosine which is periodic with periodic frequency with some small change of the phase. So essentially what you will see is so this is the solution, this is a general solution. And so what you see if you force periodically the linear oscillator, it will just oscillate at the frequency very close to its own frequency, like just it oscillates normally, but the amplitude will decrease periodically. So this is what's called beating. Okay, so that's essentially all what happens. Yes.
Qual o problema do caso que eles estão de fato em ressonância? Por que a gente não pode analisar ele quando ômega é igual a 1?
Omega equal a U. No, we can do. Yeah, if just this answer doesn't work. This answer doesn't work, and then when they're exactly equal, so you need particular solution. And let's see. This is. I think this should be a solution. For when omega is. Let's try. Omega is omega. Then let's see the x double dot will be plus omega x. So yeah, I substitute this solution. So it will give you a. So first the first derivative. So let's compute first derivative first. X dot equal a of 2 omega sine omega t plus a by 2 cosine omega t. The second derivative will be a by 2 cosine omega t minus a. So this is omega of 2 sine omega t. And if we add omega squared x, which will be omega squared x will give you a omega over 2. So there is t here. And then there is still t here. Well, when differentiate, so this is it. This is with t. And when we differentiate t, it becomes a. Okay. And x dot omega squared x is a over t sine omega t. So you see, when you sum, this term cancels, and you get exactly solution. So when you exactly resonance, this is exact solution. This is exact particular solution, and so exactly resonance, this is particular solution. So the general solution you add it with the general solution of the previous. So it's okay. Good. So the next is what happens in harmonic oscillator with dissipation. So all these analyses, it has a drawback that we consider it for a long time, and when the oscillator is observed at long time, it usually shows some dissipation. You know? So the energy dissipating. So remember what is the equation of motion for the oscillator with the dissipation is mx double dot of x plus dissipative coefficient with d positive, and then plus spring term, elastic term. And then we'll still force it. So divide everything by m. You get x double dot plus, let's put here 2 gamma x dot plus omega square x equal a cosine omega t. So the only new term is this gamma. So gamma will be d over 2m. I put 2 here because 2 is a convenient. It makes life more convenient. Okay, the situation is just the same. Yeah, so the general solution you obtain by putting particular solution plus the solution of the autonomous system. Autonomous system we already know how to solve. So the autonomous system we know how to solve, and also what is important, so I will not repeat the solution, but what is important is that the solution of the autonomous system, it goes to 0 at large times. This is because the autonomous system is asymptotically stable. Remember that we proved that whenever you add dissipation to the stable conservative system, it becomes asymptotically stable. So its solution always goes to 0 at large time. Okay, and then we also only need the particular solution. So we look for particular solution essentially. So we need a particular solution. So we need to solve, we need just to find one solution of this system. And this is, now it's not convenient to use it as a cosine omega t because we have first derivative, which will give sine. So it will not cancel in all the terms, right? So what we do, the way I like is I complexify the equation. So I consider complex form. Where the left-hand side is just the same, but on the right-hand side, I remember that cosine omega t is a real part of exponent I omega t. So whenever you take a real part of this equation gives you our system. Right? So it means that xp is just taken as a real part of any solution of that system. So we need to find this solution of the complex form and then just take its real part. And now you can try to get a solution in the form of the exponent because every derivative just keeps exponent as exponent and the exponents cancel. So we assume that the solution has a form of some coefficient, still b, no? B exponent I omega t, where b is now can be complex. Substitute it into the equation. So the second derivative gives you b omega squared with a minus, right? Because the imaginary unit squared gives you minus by b exponent I omega t. Then the second term plus 2 gamma I omega b omega t plus omega squared omega t equal a e omega t. So now all exponents cancel. And this is all is proportional to b. So we find b is a divided by all sum of these terms. So I start with omega squared. Then I put large capital omega squared. And then there remains this plus I. So we put I in front so to see that it's imaginary. 2 gamma omega. Like this, right? Let's make it capital B for some reason, because I like small b to be real. capital B. And then this is complex number. So I can just say that this is absolute value is small b and phase is psi. Right? So b is absolute value. And then we put it back. Right, so when we put it back in this expression, we get phase enters inside, exponent b is outside, and we find out automatically that the particular solution, which is real part of this, and the real part is b cosine omega t plus xi. So we found the solution, particular solution. And moreover, we know that as time goes to infinity, the solution will converge to particular solution because xa goes to 0. So everything what will remain is that solution. So when you force oscillator with it, which has whatever small dissipation, and you wait long enough, at the end you will get this solution. And what you have amplitude, and the pendulum is oscillating with the frequency of the forcing, and has some shift in the phase. So it stays with the same cosine, but slightly shifted. So its maximum minimum are not exactly when we have maximum minimum of the force. So they just slightly, it's slightly retarded or slightly. So there is shift in the phase. Okay, so what is interesting to find b? So how b depends on the frequency. So b, absolute value of b can be computed as absolute value of the b capital, right? Well, b is already like this, right? So b is absolute value of this quantity, and this you can compute as absolute value of the numerator denominator, and denominator, the absolute value is square root of the sum of the square of the real part plus square of the imaginary part. So it's never 0. It's never infinite. So it's never become infinite. So what you see now is that you still has the resonant value. And if before so let's remember what was the situation when gamma was 0. So this was an ideal pendulum without dissipation. So now the dissipation increases the denominator a little bit. So this is the amplitude of the situation with gamma is positive. So this is damped oscillator. This is undamped oscillator. So you still have a maximum which is nearby the frequency. So when you force at the frequency natural frequency of oscillator, you have large response, but it's not infinitely large. It is limited by dissipation, because whenever amplitude become very large, dissipation is also becoming large, and it starts to compensate the work done by the force. So this is it. So this is what we have with a simple oscillator. So now Let's generalize it a little bit and then we continue. So, small break. So break. Coffee, I need to go to do something. Okay, so we continue. So just what I would like to add is a simple generalization of this whole ideas to the system with n degrees of freedom, which is already a practical situation. So forced oscillations in a system with n degrees of freedom. So what we do, let's start with the conservative linear system. So linearized usually system. So let's write linearized. So what it is, it's a system which is written as mx double dot plus cx equal, and we force it, right? So f0 cosine omega t. So what is what here? So that here x is distance to equilibrium. Mass m is the mass matrix. Positive definite. C is stiffness matrix, also considered positive. So we consider the stable system. Remember, the stable system requires that C is a positive definite matrix, and then then F0 is now a vector, right? So now a vector, and X is also a vector of the same dimension n. So what you do here? So what you do is essentially something very similar to what we did with the oscillator. So first you can show in exactly the same way. So you can show the general solution can be constructed as a sum of a particular solution plus solution of the autonomous system. So the particular, and this is general solution when f0 is 0. This we know. This we already computed. So remember that xa of t, we already we know that this is its general form is the sum over all modes with arbitrary coefficients by ui. And in the case, so in the stable case, remember that all eigenvalues, the squared eigenvalues are negative. So what you can do, you can just take cosine omega I t plus arbitrary phase. So this is a way how we can write either cosine plus sine or cosine plus phase. So this is the same formula. So that's a general solution. We derived it. So what is u and lambda? They, if you remember, they should satisfy the eigenvalue problem. So which is of that form. Right? So this is a general solution of the autonomous system we found. So the only problem is finding particular solution of the full system. Just one solution is enough. So particular solution. So we just guess what is the right form. So we assume that the solution, we assume exactly the same thing what we did before. So we take b cosine omega t, where b is some vector. So now it's a vector. So you substitute, and it should satisfy the full system. So we substitute it into the system. So it will be m b second derivative will give you minus omega squared, right? Cosine omega t plus c b cosine omega t equal, oh no, not large omega, right? Frequency of the force equal f0 t. So it should be satisfied for all times. So this cancels. And then at the end we have minus omega squared m plus c b equal f0. So what we have? We can solve this solution. So if determinant is not 0, and determinant not 0 is exactly when the omega square, what you put here with minus, not the eigenfrequency, which is if omega squared is not any frequency for any I. So if there is if there is no resonance, then you find the solution. Just invert the matrix. And you get a particular solution. So that's essentially the whole story. And we can draw what it means. So you have frequency of the forcing. You have amplitude b, which is vector, so we can just take it norm. And we know that we can solve it every time when omega is not frequency of the system. And let's assume that we have like free frequencies. So this frequency each frequency determines its own resonance. And this expression gives you finite number at whatever point which is not the frequency. So this will be kind of typical graph of this system. So when you force the system, the general system, the solution will be oscillation of the system without forcing plus a specific solution which oscillates with the frequency of the forcing, and the amplitude is given by some graph which become infinite whenever you hit one of the frequencies. So these are resonances. The resonance happens when you have frequency of the forcing is close to frequency of any of the frequency of the system. And the second part is what happens if you add the dissipation. So how you treat the system. So system with dissipation. So remember what it is. We need to add a dissipative term to this equation. So it will be m x double dot plus dissipative term. And the rest is the same. So what is important is that D is symmetric, positive definite. So this is what characterizes dissipation. then the rest of the story is very similar. So the general solution is the sum of particular solution plus a general solution of the autonomous system. Also, we know that we already showed that autonomous system of autonomous solution, solution of autonomous system goes to 0 as time goes to infinity. So this is property of the asymptotic stability. Remember that we showed that whenever you add the matrix, dissipative term with positive definite matrix to the system which is stable, you have asymptotic stability. So all solutions go to 0. It means that whenever you consider general solution at long time, this part is not important, so you only need to find this. So the particular solution so again, what we do, we will make a complex form of the equation, and then we find particular solution as a real part of the complex solution solving the complex version of this equation. So it will be mx double dot plus d x dot plus cx equal a exponent I omega t. Oh, not a, f0. So we take complex form of this equation, and then we try to find solution as we did before. So it will be b exponent I omega t. You substitute it here. Well, now b is vector. Also, moreover, it's complex vector. So you substitute it there. So what you get m b double dot. So it will give you minus omega squared exponent I omega t. First term plus d b I omega exponent e omega t plus this term equal to that. So now we cancel all exponents. So what is left? Let's regroup. So every matrix is multiplied by b. So we can put all matrices outside. So it will be minus omega squared b m plus I omega d plus c d equal f0. So first thing you can see is that determinant is never 0. That this matrix determinant of this matrix is not 0 for any real frequency. Why? Because otherwise the I omega is eigenvalue of the characteristic equations. You see, if you put I omega as lambda, it's exactly this, but we proved but we know that all eigenvalues has negative real part, right? So it's asymptotic stable. So it cannot, no eigenvalue can be purely imaginary. So we know the determinant is not zero, so we always can invert the matrix. So it's your inverse complex matrix. Right. And essentially that's it. So then we find the particular solution as real part of the whole this expression. That's an answer. So if you force system with a dissipation, at large times it will oscillate with the frequency of the forcing, but what will multiply this coefficient is something which depends in some form depending on this matrix. So what you can conclude. So first of all, whenever dissipation is small, it must be close to the situation with zero dissipation, of course, just by continuity. But at the same time, you see that the amplitude is always finite, right? So amplitude is always finite. So whenever, if you define B as norm of this vector B, it's always finite for all frequencies. So it means that whenever you add damping, so if this white curve was for no damping, then whenever you add damping, you have a continuous dependence for all omega. So this is with the dissipation. So a very similar situation that we had with oscillator, but different that there can be several maxima which correspond to every frequency. And the message is that whenever you force the system close to its one of its natural frequencies, and the dissipation is not too strong, you will have a very large increase in amplitude of oscillations at that frequency. And this you often see here in auditorium because there is a ventilator below. What happens? So you can change frequencies of these windows by opening it. So depending on how you open, is different frequency, right? And if you open at such a place so its own frequency, one of its frequencies coincides with the frequency of this oscillator, which give a forcing, it starts to give a noise because it's exactly you get oscillations which are very strong. So the way how you avoid is you move the window and you get out of the resonance, and then it start making the noise, stop making the noise. Or if you press the window, you also change you shift eigenfrequencies, so you have to your frequency of the forcing just should not be close to one of the eigenfrequencies. So that's how you avoid resonances. And in particular, this is why the analysis of the eigenfrequencies is a very typical test in engineering, because knowing frequencies, you know how to avoid resonances or how to be in the resonance, because sometimes we may want to be in the resonance. Okay, so this is the end of this part, which is I think is simpler. So the next part will be parametric resonance, and for that part I have a typed PDF with a note. So if you take my webpage, so you find it. And I will just start this topic. And then we will continue analysis tomorrow. So this part is harder. So this is what's called parametric resonance. Parametric resonance. So what's the difference? So the difference is that in the previous case we were considering directly forcing. So you have periodic force acting on the system. In a parametric resonance, what changes periodically in time are parameters. So for example, coefficients of this matrix or coefficients of a matrix. So let's see some examples. So the simplest example is what we already had. You have a pendulum. In a gravity, and then you have a support which moves kind of periodically in time. So it's like, remember, minus a cosine omega t, for example. Do we use large omega? Do we use, yeah. Periodically moving the support. So what is changing? So it's not a force that moves, that changes, but it's just position changes periodically in time. So and as a result, remember what was the equation of motion? Equation of motion, I will just draw you directly. So equation of motion was phi double dot plus omega let's write it in original form. So G over L, so gravity over length of the pendulum. And then it was 1 plus second acceleration of the support divided by J. Sine phi equals 0. So this was one of our first lectures. And now you just substitute this, and you get phi double dot plus G over L, 1 plus minus second derivative will give plus. It will be A omega square over G cosine omega t. So what we have is that, you see, is a coefficient changing periodically in time, not a forcing. So this is different. So the forcing would be outside, but here it's a coefficient which actually multiplies some of the terms of the equation. It changes parametrically in time. So parameter changes periodically in time. So automatically, of course, you have no energy conservation, of course. Remember, the energy conservation required that the Lagrangian system, Lagrangian, it does not depend on time. You can write it with the Lagrangian, but Lagrangian will depend on time. So there is no energy conservation. Okay, so this is a system we want to see, and there are other examples. And one of the examples that I'm going to show. Sorry. I'm going to show is that it's very simple to this. So imagine that you have a fixed pendulum, fixed support, also in gravity. But now what you change periodically is L changes periodically in time, so the length. There are different ways to do this. One way is you put your cord through the hole and then just pull it up and down. So this is how you can do it at home. Another is a swing. I think you never saw this swing here, but I will show you a video. So it's a swing. It's a very big swing. It's a swing where you essentially where you can stay And then the way how you use it is that you're actually stay when you're in upper position in any of the two. And you sit when you're in a lower position. Does it look like, no? So essentially what you do, you stand when you're when you get up, then you sit when you're in the middle, then you stand up. You stand up, sit in the middle. So the question is it helps you to swing or not? So usually, in usual swing, you go forward when you are here and backward. No, you go backward when you're here and forward when you're there. So this is a usual resonance, because this is a way how you put a momentum periodically in time, right? With a period which is close to the period of the swing. So this is the usual resonance. But this is different, because this is you see, you sit and stand, so you don't put a momentum. You just change the length of the pendulum, right? So you put your center of mass lower, upper. You just change the length of the pendulum, and you do it with a period with twice smaller period, because when the pendulum just make a half a period, you already did the full period. Another half a period, you did another full period. So your frequency, you do it with a double frequency of the pendulum. And this is essentially the whole parametric resonance in words. So we will see if it works or not. And then there are many other applications. For example, you can see the ships, when it goes on waves, also there big waves just put it up and down, right? So that's kind of direct realization of the pendulum with a moving support in more complex form. Or then there is a similar problems when you have earthquake. So it's also the moving support or up or down. So the foundation moves. So it's also, so these are situations where it's not a force directly which is applied, but the parameters change periodically in time. So this is a large class of system which we'll consider. And you'll see that there is still a phenomenon which is called resonance, but it's very different. I'll just show you how you can use this swing in this form. Did you see? You saw it, no? I have it. You can find it in YouTube. It's, I think this is a national type of swing in Finland. But I also had it in when I was a child. I never saw it in a real. Huh? Yeah. No, I don't know if I can show. I guess I can show YouTube videos if we save it on YouTube. This is not forbidden. No? So the way how we do is okay. Well, they call it kicking. Let's try to see if it works. Oh, it's quite fun to see. So, YouTube video. You just take. So you see, it's stand up and sits. So it's the only it doesn't put a force. It just change. Well, it doesn't make a momentum to the pendulum. It just changes the length, the distance between the center of mass and the support. And this is very effective. It's actually with this type of swing is much more. You will not be able just to do it just going forward and backwards. Don't try to repeat. Okay, good. So successful. Okay, so let's start the analysis. So how we analyze? We will start the analysis with that first with that pendulum equation, and then we'll see that what is the general system that leads to the parametric resonance. So first idea is very similar. So what we do, is we reduce the second order system to first order systems, because essentially what we will be working with is the ordinary differential equation with coefficients which depend periodically in time. So the usual ODE, ordinary differential equation, is written in the first order form, so this canonical form. And let's put this equation to that form. And remember how you do. You just take new you define a vector with two components, where the first component will be angle, second component will be velocity. So let's call this phi. Yeah. So now the first, and now we can find the equation for the derivative for this vector. So first component is just a definition. And then the second component, phi dot, double dot, it's this expression put on the right. So it's minus g over L 1 plus a omega squared g sin omega t sin phi. Psi dot, which is second derivative, is this. So now the whole right-hand side, we can just say that this is some function which depends on y and depend on time. Yeah? Depend on y because both components enter. but also it depends on time. So in other words, we have the system which has this form. It's ordinary differential equation, but now it also, the right-hand side depends on time. And there are two properties that we will keep. The first property is that two properties. The first property is that we assume that epsilon, that the epsilon 0 is a solution. Is equilibrium. Is equilibrium. So it means that g of y0 t is 0. So our equilibrium here is clear. What's our equilibrium is 0, 0. Correct? 0 position, 0 velocity. So that's the equilibrium. So if it's straight, it doesn't move. So in general, this is general form. So for general function j, so we will assume, just put this assumption. And second assumption is that is a periodicity. Is that g of y at any y at time t is equal to g at y at time plus period. So periodicity. So in our case, our period comes from cosine, so it's just 2 pi over omega. So these are two conditions, and under these two conditions, we have to solve this system, and we will do generally. So we will not just apply it to this system. Later we will consider this system, but for now we will just see general properties of that equation. So what I will need 0, so let's write star for the equilibrium. Equilibrium will be y star. The equation is in general quite complicated because you cannot solve, there is no general recipe solving, well, actually the recipe that there is what I am going to show, but usually you cannot solve explicitly equation with periodic coefficients. For example, this equation does not have analytic solution, or in other words, actually the solutions of this equation have a name, so that you can just name the solution. So usually people give name to the solutions, but you cannot express them in usual functions that we're used to. So what we will do? So how you solve these systems? There is a very convenient trick which is called Poincaré map. Poincaré map will directly use this periodicity condition, and what you do is consider the time evolution. In time evolution, so at every time you're in a at some point y in there. So let's assume that here we can take y from n-dimensional space. Our n is 2, but in general n-dimensional. So consider your solution is a graph which depends on time, and a point lies in this space Rn. In our case, it's just R2. So our point is just two values, phi and psi, velocity and coordinate velocity, and it depends on time. So solution is something like this. We start for the initial point, and this is our solution. So this is y of t. Now let's take into account that system is periodic. So there is 1 period, 2 periods, 3 periods, and so on. So let's see where the solution is at each period. And what we will do is more or less every plane is y on array. So what we will do more or less is that we will act like making photographs shots at every period. So the initial point we call y0. Then at one point at one period we call it y1. At 2 periods we'll call it y2, and so on, y3. And we will forget what happens in between, but just make these snapshots every period. So in other words, what we define is this yk is y at k period. But the evolution is given by deterministic differential equations. So what you can say is that you can define a function f which maps. You can define a function we call f of y such that it maps an initial point to the point at period 1. So y1 is function of y0. So this function will give for any initial condition, it gives you the value which you obtain in the period. So this function exists, it's unique, so that's only the theory of differential equation tells you that under certain assumptions this function exists. But now what you can see that the evolution from 0 to 1 period is exactly the same as from 1 period to 2 periods, because the system is exactly the same here and here because of the periodicity condition. Yeah? So this periodicity for any y and t. So the system at every period is behaves exactly the same way, which means that the relation between y1 and y2 is also given by the same function f, and the relation between y2 and y3 is given by the same function f. So which means that every yk plus 1 is obtained through exactly the same function from the previous yk. So this function is called Poincare map. Good. Okay, so that's already a simplification, because it shows that if you just analyze system within 1 period and find how the initial condition maps to the condition time t, you know with the same function you can know what happens at any number of periods, because you just iteratively use the same function. So so what happens in between doesn't matter. So we can just see what happens at. It's like you're filming with this period with interval between shots equal t capital, and then you just see it every moment. But you know that. But using this function, you will know what you will see at every next period. And this is simpler. You see, so this is simpler because here we kind of disconsidered the full interval and only considered some discrete points. So this is called discrete dynamics. Because now our time is integer number. Right? So instead of using continuous time here, we now can use just discrete time, which is counting number of periods that pass through. And also what is good to see is that if y star is equilibrium for the continuous system, then y star is equilibrium for a discrete system. So this is essentially obvious, because if y star, which was just a constant solution, right, so it's exactly the same. It's exactly the same point at each plane. So the map F just maps it to the same point. Fixed point. So equilibrium for the Poincare map is just point which does not change under each iteration. Okay, very good. So we have two. Essentially, what we have two different descriptions. We have two different descriptions: continuous time this is system, and equilibrium means that this function right-hand side is 0, and discrete time and the equilibrium condition is that f of y star equal y star. And these are two different ways to see the periodic system. Here we look at all details of the dynamics, and here we look at the details only. So the connection between the two is given by the yk is y of kt. So here we see only on integer number of periods. So I think I better stop here, because now we will go into details, and better I'll do it all tomorrow at once, because otherwise I will have to repeat it anyway. Yeah, so let's stop here. So for tomorrow we will start analyzing the system, and we will describe this the question of small oscillations near equilibrium, stability theory, stability criterion, and all the details we had for the autonomous systems actually can be carried to the periodic system exactly through this duality, that for the continuous time system where we have time dependence, we can define discrete time system where there is no time dependence. So the discrete time is autonomous system. There is no time entering to the right-hand side. And since there's no time entering to the right-hand side, we essentially can use the same approach as we used for autonomous systems before. And then we can carry it back to the continuous time formulation. Okay, and so that's our